Hi there. In this tutorial, we will delve into what consistent hashing is, why it's crucial for distributed systems, and how it works to ensure efficient and reliable data distribution. So, before proceeding with consistent hashing, we need to know what actually hashing is. So, we can imagine hash functions like something that processes an input and gives an output like a normal function would do. So there are hashing algorithms that are used to hash something. Like, let's say, here I am taking an input string a and I'm applying the hash function, and the result is 54. Let's say I get the value 54. Now we need to store this hash value. So this is called hash value, by the way. So we need to store this hash value in a hash table. So what is a hash table? It's a data structure that has a fixed number of slots, 1 2 3 4 5, or you can name them as buckets. So let's say our hash table has 5 slots, and to decide which slot to use, we use the modulus operation here. So the modulus operation helps us to map our large values of, there might be large values of hash values, and we can map them into our available slots so that they are contained within this range. This is called the hash range. So we are doing 54, which is the hash value, and we are moduling with 5, and we get 4. So we will be storing the input a onto fourth location, fourth index, and we are storing a here. And this is how we store inputs into a hash table. Now the hash table might become full or might be too slow to handle the increasing volume of data and queries. So to overcome this problem, we have a solution which is called horizontal sharding. So coming to horizontal sharding, so horizontal sharding is a technique where we distribute the data across multiple independent databases or servers, which are called shards. So each shard will hold a portion of the data, making the system more scalable and efficient. So I have an example here. Let's say this is a table, and you can imagine like a customer table. It has a cust ID, which is the customer ID, the name, the email ID, and the item name. And the customer ID has an auto increment feature, which is uniquely identified, and it goes from 1 to this number, and here's the name, here's the email ID, and so on. Now, okay, this will be email. Yeah. Now what happens is we can distribute the data across two tables, and we can consider these two as separate independent databases, and we can distribute the data like we can count the cast IDs from 1 to 500,000 in one table, in one database, and the other starts from 500,001 to this. So as you can see, we are separating, and we're separating the data, and we shard them across multiple databases. So by spreading the data across several machines, we reduce the load on a single database, and it helps improve performance and ensure that we can continue to grow without hitting capacity limits. So this approach allows us to manage large amounts of data efficiently and handle higher loads, keeping our system responsive and scalable. Now imagine your system is growing rapidly and you need to add new servers to accommodate the increasing load of data, right? So here things can get a bit tricky, because when you add a new server, you will need to distribute the existing data, right? You need to redistribute this, also ensure that the workload is balanced across all the servers, because you don't want to overload a single server, right? So redistributing data can be a bit complex and also time consuming, especially if you have a large data set, and the rebalancing strategy needs to be revalued at each step. And the main issue is with the rebalancing, and here comes the concept of consistent hashing. So here we have an approach that makes sure that the data that is coming is uniformly distributed, not quoting uniformly, but almost. So we will come to some modifications to it, but currently we are assuming that we have the consistent hashing as an as a solution to uniformly distribute the data. So you can imagine the keys for these hashes. You can imagine the keys to be starting from 0 1 and it goes till n. And if you join these 2 points, we can consider a hash ring here. So basically you are dragging this point and you are connecting it to it, so we can conceptually imagine that this is a hash ring, right? Now what is the use of this hash ring? So here we can assign keys to specific servers, and I will show you how the procedure works in consistent hashing. So let's say I have the server placed here. I have server 1 here. I have another server placed here, server 2, and I have another server placed here named server 3. And correspondingly, I have the keys k1, and let's say I have another key k2, k3. I have k4 here, right? And I can also have k5. Yeah. So what we do in consistent hashing is we rotate clockwise, right? And by rotating clockwise, we make sure that all the requests served under a particular set of keys are mapped to the closest server. So what do I mean by that? So in this case, let's say I start from 0, we have k5, we have k1. The very next key is available after a server, right? So we are getting a server. The closest server to these two keys is s1, because we're starting from k5. So these two keys get mapped to s1. So the number of requests coming in between these will be served by s1. Now we go on as usual and we see k2, we see k3, right? And as you can see, k2 and k3 will be served by s2. Similarly, we move on and we find k4 here, and k4 is mapped to s3. So as you can see, we have a better method of distributing the data. So it's like going clockwise, and whatever server comes first will be serving these requests. So I want to show you an example of how consistent hashing helps us, reducing the amount of rebalancing that we need to do if a new server is added or a new server is removed. So let me just take a similar example here. We have k1, we have k2, we have server 1, we have k3, we have k4, we have server 2, we have k5, we have k6, and we have server 3. So let me just map them. S1 will be mapped, let's say I start from here. So k1 k2 will be mapped to s1, k1 k2. We have s2 serving, we have s2 serving requests under this batch, which is k3, k4. Then we have s3 serving k5 and k6. Cool. Now let's say the load has been increased and you want to insert a new server. So let me just map the older one here first. We had k1 here. Now you want to add a new server. So let's say I want to add a new server at this position. Let's say I have s4 here as at this position, right? Now let's remap everything. So server 1, k1 and k2, we are rotating clockwise, of course. Then we have s4 here. It has got k3. We have s2 getting k4. We have s3 getting k5 k6. right? As you can see the change in between the mappings and the rebalancing. So S1 and S1 there is no change, right? We have the change in S2. As you can see, we have a new server S4. So K3 won't be mapped to S2 anymore, it will be mapped to S4, but there is no change in S3 again. So as you can see the change is very minimal, the rebalancing is very minimal here. Now what happens when we remove a server? Let me just draw the same. So let's say I want to delete a server. Let's say I delete S1. Let's say I delete S1, and now let's remap the entire thing. So S1 is no more here. So we have S2, K1, K2, K3, K4. We have S3 getting K5 and K6. And as you can see, um, again only S2 has a change, and obviously we don't have S1, but S3 remains the same. S3, K5, K6, K5, K6. So as you can see the change is extremely minimal in terms of rebalancing, and this is where consistent hashing helps us. Now you might remember that before starting I gave a disclaimer that we are considering this to have an uniform distribution, but this is not the case always. Let's imagine there's a social media platform where user activity can vary significantly. Of course, there might be influencers who are very active, creating multiple posts, comments, likes, while others might be less active while interacting with the platform. And when users interact with the platform, their actions, let's say, generate data that needs to be stored and managed. For example, when a user creates a new post, an unique post ID is generated by the system to identify that post. Now, active users who create multiple posts contribute more key generation events compared to less active users who create fewer posts, obviously. And consistent hashing is used to distribute the keys, let's say the post IDs, across backend servers. So let's say let's say there are many post IDs. Consistent hashing will be distributing them into like several servers. 1 2 3 4. So it will want to ensure a balanced workload distribution. However, the distribution of the keys is based on the generated keys themselves. Like if certain users are highly active and generate a large number of keys, so by keys I mean the post keys which are generated from posts themselves. So I post something, I generate the key, and these keys might be concentrated in specific ranges handled by particular servers. So let's say like there are three servers and one of them is getting overloaded because they are getting redirected. So this results in uneven request distribution, and as a result of the uneven distribution of the keys, requests generated from highly active users will be considered on the servers like this one, right? And servers responsible for handling keys generated by highly active users may experience large volume of requests compared to the other ones who are like less active users. So this can lead to uneven server loads, and obviously there will be potential performance issues. And to solve this, the solution is vnodes. So instead of directly mapping servers to hash ranges, we create multiple virtual nodes for each physical server. So there might be virtual nodes which are distributed across the hash space. So we had several servers, right? But right now we will be having uh, more like granularity in the number of server contents, because this helps in better distribution of the data. So there can be vnode here, vnode here, vnode here, and so on and so forth. These are virtual nodes which refer to the real nodes. Now Let's consider a scenario. Let's say we have three servers A, B, C, and this server A, server B, and server C. And let's say each of them has two virtual nodes VA, VC2. Now imagine a scenario where server A experiences a sudden spike in user activity. To prevent the overloading in server A and ensure even workload is distributed, vnodes help here. So the entire system dynamically redistributes these vnodes to balance the load across all the servers. For instance, some vnodes from server A might be moved to server B. So let's say these move to server B, and some vnodes from server B will be moved to server C. So this helps in better distribution of data and helps reduce workload on a single server. So this is how consistent hashing works. This is how we modify consistent hashing, and I hope you know why we are using it. Starting from hashing, we are moving to horizontal sharding, and then we're moving to consistent hashing, and then we're using the concept of vnodes. So I hope you like this video. Drop a like. If you have any doubts, you can post it on the comments section, and thank you.